Okay, I'm thrilled to be here. What a wonderful gathering. I think everybody said everything, so there isn't much for me to do. But what I'd like to do is two things. Fab Labs aren't a point, they're an arc. So I'd like to talk about the arc. Where did this start? Where is it going? We're at this point on the curve, and I want to talk about the curve. And then I want to end with a homework assignment, a challenge for all of you. So there's a revolution coming. You've seen all the stories about 3D printing changing the world, but that's not the revolution. In fact, those of you who know me know I don't like 3D printers. These stories are written by people who don't use 3D printers about things they don't really know about, but reproduce each other's stories. It's sort of like this. In 1950, when microwave ovens were invented, there were stories about the kitchen of the future. And you're going to make all your food by pushing a button in the microwave oven. Yeah, microwave ovens are okay. You have them in the kitchen, but they don't replace the kitchen. So 3D printers are not why we're here. In 1952, MIT made the first computer-controlled milling machine. This is one of the first real-time computers ever, and they had the idea you could connect it to a machine and turn the knobs to make things. So that's where it started. And this is the present. Today, there are maybe 20 computer-controlled processes that descended from that. With the computer, you can cut, you can turn, this is a laser, this is a plasma, this is a jet of water, this is cutting with a wire, this is bending, molding, this is weaving, this is casting, depositing, extruding, dispensing. All of these have the computer moving a tool around that does something. And all of these are useful. The 3D printer, as you know it, is one of these, but there's 19 other ones, and they're all very useful. They all descend from here. This is Norbert Wiener, and he invented cybernetics and had the servo mechanism laboratory. And that's where this idea of a computer controlling a machine first started from. But at that same time, there were two other revolutions. So this is Claude Shannon, and if you've never read it, this is the best master's thesis anybody ever wrote. This was in 1940. And in his master's thesis, he invented digital. This is the thesis where he showed what it meant to be digital. And then he went to the phone company, and it turned into the theory of information theory. And what he did was show that if you communicate with a symbol, as the code gets bigger, the error decreases exponentially. That's called a threshold theorem. And that exponential means it's so fast that even though the hardware is imperfect, you can communicate perfectly. So that's what Shannon did. Before him, a telephone degraded with distance. After him, we have the internet, essentially. So that's the first digital revolution. Here's the second digital revolution. It was John von Neumann. At the time, computers were analog. Your answer got worse with time. Von Neumann showed if you compute with symbols, you can compute perfectly even though the computer is imperfect. And so that's the second digital revolution, showing how to compute perfectly with an imperfect computer. Now, the digital revolution in fabrication is a little older. It's actually 4 billion years old. This is my favorite protein. It's the ribosome. It's the machine that makes you. It's a molecular machine, and it's programmable. And what comes into here is a program that codes the construction of you. And to understand the ribosome, think about a child playing with Lego bricks and compare it to a 3D printer. The coordinates come from the bricks, which means the child can make something bigger than themselves. The 3D printer has to measure position. When you assemble the bricks, they reduce errors, and so the structure you make is more accurate than you are. If you've used a 3D printer, you know errors accumulate, and if something happens on the bottom, it goes all the way to the top. And when you're done, you don't make trash. With Lego, you disassemble it and reuse it. With a 3D printer, you put it in the trash. Those are the properties of a digital system. That's how you work. And so what's emerging now is we went from analog to digital in communication, analog to digital in computation, computers controlling machines. Let's see. Computers controlling machines dates back to 1952. The revolution isn't additive versus subtractive, it's analog versus digital. The real research of which Fab Labs are a point is how to put codes and programs into materials. So what I want to do now is show you a little bit about what that research looks like. Then I'll come back and talk about what it means today. This is a meeting I ran with the White House about a month or two ago. And I was in Washington, and every single government agency wanted to talk about 3D printers because they read about it in the newspaper from people who use them, who wrote about them, who don't actually use them. And I got so annoyed, I proposed with the White House Office of Science and Technology Policy, we'd have a meeting with all of the researchers and all of the agencies to talk about where the technology is going. And just what came out from that is there's this roadmap from computers controlling machines to machines making machines, to putting codes in materials and programs in materials. So I'm going to take a few minutes to show you what each of those stages look like, and then what does it mean today. So in the first generation, there are a number of machines you've heard of, like the RepRap and the MakerBot. What's emerging now at the stage after that is rapid prototyping of rapid prototyping machines. This is a series of machines we've made where this one dispenses, this cuts with multiple axes, this one prints, this one turns, this one slices. What's interesting about these machines, though, is what's underneath them is structural systems and programming systems and a whole set of technologies. So making the machine is as easy as making a project. So rapid prototyping of rapid prototyping machines. These are machines that make their own parts, and it becomes as easy to make a new machine as to make a project on the machine. Here's one of the first ones was, this is Jonathan Ward, and he made this snap-together machine. That inspired this machine, which is instead of fasteners, it's self-aligning. It's flexural alignment. So all of the tolerances come from how the parts are made. That machine spun off, and now that's being, this was a very successful Kickstarter launch. If you were at Maker Faire, you saw this one is now being commercialized. Another one that came from this project was born with the people involved and now being commercialized is the Form 1 printer, another very successful Kickstarter project. I think that was one of the largest ones. Then this is a really neat one. Two students made this machine, which is a complete fabrication laboratory in a briefcase. So it pops up. It's got kinematic couplings that maintain tight tolerances. You snap in, but it aligns all the parts. And then this one has interchangeable heads. So with one head, you can print. With another, you can cut. With another, you can mill. So it's a complete briefcase-size printing facility, and it fits as carry-on luggage. And so then another machine in the project asked, what if you wanted to do large format machining but make it portable? And so they made this really neat machine, which is a portable large format mill. And it uses what's called a Saurus linkage, which is flexural hinges instead of bearings. And again, it uses the same kind of flexural self-aligning joints. And so you can go into the field and take it on a picnic if you'd like and do large format machining. So those are what some of the machines look like of the second stage of instead of buying a machine, rapid prototyping of rapid prototyping machines. One of the goals for Fab Labs next is you go to a Fab Lab to make a Fab Lab. And in the next year or two, that's coming. Then supporting that, we had to rewrite CAM because controlling the machines assume the person who designs something is different from the person who makes it. and we had to rewrite it so that it all happens in one place. We then had to rewrite motion control, so your design controls the machine directly. And more recently, we've been rewriting CAD because there's a lot of history in separating design from manufacturing. And so these are new user interfaces for how you design stuff that talk directly to the machines. This is another one of these new user interfaces. So all of that is where we are today. In the next year or two, we're going to move from buying Fab Labs to going to a Fab Lab to make it. Then the step after that is assemblers, going from analog to digital materials. So this, as an example, is micro parts, micro Lego for electronics. Today, to make a circuit board commercially, you etch it, and it's hard to make many layers and route it. Here, this is conducting and insulating Lego parts that you snap together and make three-dimensional circuit boards by a snap-together process. And so the wiring and the interconnect is all done in one go, and you can disassemble it and reassemble it and make complex 3D shapes. And so that's electronic Lego, and what we're beginning to do is, in stages, move towards making whole integrated circuits this way. This is another kind of Lego where instead of little parts, what we're doing is making carbon fiber composites to show if you want to print an airplane, the way to do it is not extruding plastic, but snapping together carbon fiber composites. And we recently showed these snap-together composites are the world's lightest, strongest material. They have amazing properties. Okay, so that's step two. Step one is you go to a Fab Lab and make a Fab Lab, and that's in the next year or two. About 5 years away out, you'll go to the Fab Lab, and instead of 10 different machines, you'll have one assembler that'll assemble micro Lego. And then the step after that is, this is the mathematics of coded folding. When you're made by the genetic code, the design file actually becomes you. The code becomes a shape. And so we develop ways to take 3D designs, put them into codes where the code turns into shapes. And then we made a number of different systems. We made robotic systems macroscopically of shape-changing robots. And then microscopically, what we're doing is we're making proteins that implement that mathematics. So these are DNA bricks, and they implement that coded folding. And so the 3D printer becomes a nano-assembler that folds nanostructures. And so eventually we end up with materials that change shape. And so that's maybe 20 years of work to get to that point, where you have truly shape-changing materials. Now, that's a peek at the research. What does it mean for today? In the beginning were mainframes, $1 million used by a corporation. Then came mini computers, then hobbyist computers, then PCs. You can line that up roughly as the 1952 milling machine was like a mainframe. And the machines in a lab like mine are today like that. $1 million, you need a big organization. The Fab Labs are like mini computers I'll tell you about. The machines that make machines are like the hobbyist computers. And the personal fabricator coming is like the PC. So to look at what that means, this is one of my favorite pictures. This is Ken Thompson and Dennis Ritchie at Bell Labs. And what they're doing is inventing Unix. This is the moment when modern computing happened. You can essentially trace all the things you do on a computer to this moment. The internet, video games, word processing, all happened coming out of what they're doing in that picture. And what made it possible was the mainframe was owned by a corporation. The mini computer was owned by a work group. A group of people could own one. It was hard to use. This was a processing rack. This was a storage rack. This was an I/O rack. It was a bunch of different things you had to plug into each other. But because a group of people could own it, not a whole corporation, modern computing happened. Then these hobbyist computers, those were life-changing for people like me. When they came out, the killer application was you would flip switches on the panel to load a program, and then you would run it and the lights would blink. That was it, and it changed the world because that was the first computer you could own by yourself. It wasn't yet really useful, but you could own it. Then came the PC. Now the PC, if we compare it, a 3D printer isn't a PC. A 3D printer makes a piece of plastic. In the PC, all of these different functions were integrated. In the PC was a graphics system, the processor, storage, power, I/O, display. All those functions were integrated in one system. So the personal fabricator takes all these different functions and puts them in one box. That's still a number of steps away. But the lesson from the picture and the way to understand Fab Labs is the internet was invented here. And so what you heard about today, what's happening is this is the moment analogous to the birth of the internet. The internet went from 1 to 2 to 4 to 8 sites. Popularly, it seemed like, boom, it just appeared, but it had been doubling for many years. In the same sense, the internet didn't wait for the PC. It happened in this stage. So the technology in a Fab Lab, if you view the whole thing as one machine, lets you make almost anything. Over the next 20 years, it's all going to get integrated at this profound level, but you don't need to wait 20 years. You can do the applications today, invent if anybody can make anything. How do you live, work, and play in that world? And so where Fab Labs came from, for my involvement, was we had spent a lot of tax money in the US at the lab I run, and the government at some point said a rule was passed, you have to show social impact. And so Congress said to the National Science Foundation, show social impact. NSF didn't know how to do it, so they turned to us and said, show social impact. We didn't know how to do it, but we thought the machines were pretty cool. So we set up a community lab with a little version of the big machines, and our whole vision was one lab just to shut the NSF up, and then we go back to work. So this was in a community center in Boston. But there's a strong connection between Ghanaian community in Boston, and they brought a lab to Sekondi Takoradi in the coast of Ghana. Then there's a strong South African connection to Ghana, and this was a lab in Soshangovi outside Pretoria. And then there's a strong Indian connection. This is Pabal in western Maharashtra. And then this is Jalalabad in eastern Afghanistan. And you can't wake up in Cambridge, Mass. and decide rural India or a war zone in Afghanistan needs precision fab tools. But every time we opened a lab, somebody else wanted one. And so they started spreading virally. Now, in these Fab Labs, one of the key things is they all share the same base set of capabilities so that anybody can make almost anything, and people and projects can be mobile in the network. So in a Fab Lab today, the most beloved machine by far is a laser cutter. You cut out parts in 2D, you snap together to make 3D things, and it's fast and the materials are cheap. I'd say the second most beloved machine is the large format mill, that you can use it to make furniture, boats, bicycles, large molds for casting, composite tooling. Maybe third most beloved is precision machining that lets you make circuit boards and tooling. I'll show you examples. Sign cutter for printing flexible circuits. There's a 3D printer and they get used, but maybe it's the fourth or fifth most used machine. There's some things it's good at. It's slower than the others, and the material properties aren't as good, but there's some things it's good for. Then 3D scanners, molding, casting, embedded programming, electronics. So just some examples of processes you can do in a Fab Lab. One of my favorite ones is you mill wax, you cast rubber, and in that you cast parts. So here's a cleat, here's a chess set. And done that way, it's a better surface finish, lower cost materials, faster production, than 3D printing for things for which it works. This is laser cutting. Here you make a boom box. With the precision mill, you make circuit boards and program microcontrollers, and you learn to use a range of microcontrollers and a range of programming workflows. Using the computer-controlled knife, for example, making flexural materials, large format machining, and then composite tooling and laying up composites are all examples of what you can do with the tools in a Fab Lab today. To understand in powers of 10, a lab like mine at MIT has $10 million machines for this fundamental research on things like molecular assemblers. Within it, there's a workshop that has $10, $100,000 machines, these high-end manufacturing tools for physical fabrication. The Fab Lab has roughly $10,000 tools, and that's enough not just to make things, but to make machines. And with those, you can make machines that look like these in $1,000 in parts. And with those, you can make these for hundreds of dollars in parts. And so you should view this not as any one of these wins, but each has value. This is great because it's a little thing that makes something. This is nice, a little more expensive, that makes something useful. This is so valuable because this not only lets you make stuff, it lets you make other machines. And then these are the tools beyond that that let you develop these capabilities. And so think of it as a hierarchy of capabilities. So all the labs share those, and from the first, we're up to about 200 now. They've been doubling every year and a half, so there's about 200 coming. And you heard some of them. Eddie's lab in Manchester, the reason I like this one so much is the Industrial Revolution started there. At one point, Manchester had 3/4 of the world's mills. Now it has 2 football teams, but not much industry. And the innovatives there are really developing a whole new notion of business where with these tools you can go to market by shipping data. You don't mass produce a product in a factory. You design something, you can ship data, and you can produce it all around the world, really creating a whole new economy, a whole new notion of industrial revolution. The Vogue lab was a derelict. The most beautiful building in Amsterdam was derelict. The artists took it over, have this wonderful Fab lab. And I love this project. With the large format mill, you make the furniture. With the precision machining, you make the tooling. Darth Vader can play against Michelangelo's David. You make the electronics to keep score and watch the replay. You know, it's a wonderful project, you know, and a great example of what could be a business. This was the lab in Barcelona. Tomás, who just had to take off. They were interested in, can you make a full-size house the way you make a playhouse? So this is using the Fab Lab to do rapid prototyping on the scale of solar housing. And they made this gorgeous house as a rapid prototyping project. So rapid prototyping using these tools, but now making housing. And the really interesting thing there is they're now running the city. The history was Vicente wanted these machines, and to get the machines, he needed a place to put them, so he needed a warehouse. To get the warehouse, he needed something to sign the piece of paper, so he invented the Institute for Advanced Architecture Catalonia. It didn't exist, it was a made-up organization, so he could have a warehouse for his machines. Then they had the warehouse, they had to figure out how to pay for it, so they said, well, let's make a school. And so that's where the school started. And the Fab Lab flourished. But what's happened since is Barcelona has this wonderful design style and 50% youth unemployment. Just the economy is broken. A whole generation doesn't have a chance of a conventional job. But they spend money on products made far away that comes in ships in the harbor. And they describe the city as products in, trash out. It's a product-to-trash conversion device. Boats come in the harbor with products made far away, and you turn them into trash that goes to landfill. And so they had a vision of changing the economy, and Vicente now is the city planner. He's the architect. Tony is now the deputy mayor, and their buddy is the mayor. And what they're doing is they're filling the city with Fab Labs as civic infrastructure. So the city is globally connected for knowledge, but the goal is self-sufficiently locally. Skills and jobs are local, and you produce what you consume. And so the Fab Labs become a crucial part of the civic infrastructure. This is President Obama visiting one of the labs. Bill Foster is one of the 2 physicists in Congress. And in the US, he recently submitted legislation to make a national lab out of the local labs. We have national labs that are these billion-dollar places that don't directly help people. The immediate connection is remote. The idea is to take community labs, and any one of these labs doesn't know enough to do all of this, but make a national lab out of local labs as part of the national infrastructure. So very interesting legislation. So as this network has grown, the community has grown. Once a year, all these labs come together. This is going to be in Japan in August, and that's the best chance to come meet the network. And what I love about this meeting is there's rich people, poor people, north people, south people, rural people, urban people. There's Sunnis and Shiites, Protestants and Catholics. floppy connectors. You should have back. There are all these different, but they're all the same. They're all makers. All the languages, all the cultures, the people work and think the same. And so there's this wonderful gathering of all of them once a year. And then to keep up with this growth, this is much too big as an outreach project. And so what's now emerging is a series of organizations, because conventionally aid, education, industry are all done as separate segments. This sort of turns it on the side. Anybody can make anything. So rather than going to work in a factory it's sort of punitive, and then go home and have fun, you can make what you consume. They can all be integrated. So to keep up with it, we found we have to create a lot of new organizations. There's a network of regional foundations to help support the logistics. And I asked at lunch about creating one of these in Italy, and you kindly agreed to help start it. So we'll be launching one of these programs in Italy to help provide the logistics to start the network, if that's okay to say. We're creating funds to invest in the businesses, and one of the ones that is most important to me is the idea of the Fab Academy is we had amazing kids come through the labs far ahead of the educational opportunity in their schools and then falling off an educational cliff. And so rather than taking them far away, in the labs, they have access to all these capabilities. So the way the Fab Academy works is students have peers with mentors in work groups in labs, and then they're linked globally for online content sharing and lectures. But it's like an internet. It's a distributed network of education to provide mentoring. And so a lot of the effort now is the technology is humming along nicely. We're finding we have to build a whole new set of organizations for this new kind of economy we're creating. The jobs aren't coming back to where they used to be. We're creating this new economy and we need new organizations. So with that, I'm thrilled to have Maker Faire coming here. I love the Make community, but the challenge and the opportunity is do it yourself can lead to reinventing old mistakes and doing dumb things. The real opportunity is doing it together, collaborating and mentoring, and embracing this breadth, but providing pathways to go from easy to hard things, and really reinvent what is education, what is governance, what is industry in this new world of digital fabrication. And so the challenge I want to now leave you with is I had breakfast with the US ambassador this morning, and I had lunch with a number of people from Italian government ministries, and they all asked the same question, which is, the old way isn't working. Trying to fix the old economy is broken. This seems like a new economy. What do we do? And my advice to them was empower all of you. Don't try to figure out the policy and programs. Give people the tools and let them do it. Invest in the infrastructure. And so my suggestion to them was fund Fab Labs. Give people the means to do all of this and then stand back and let them figure out how to make the businesses and how to organize. And they said, sounds good, okay. And in turn, then my suggestion was rather than picking winners, what they should do is ask the community to propose where these go and how to do it. And my suggestion to them was they shouldn't do like a call for proposals, because generally the people who do this aren't proposal writers. They should just find interesting sites and empower them with access to the tools. And so they said, sounds good. And so the challenge to all of you is there's real interest from the stakeholders, from the embassy, from the ministry, from businesses in investing in these, if you can figure out how to tell them how to do it. And if you, rather than writing a proposal, if you can tell them how to set these, where they go and how to set them up, there's interest in investing in the tools. And so there's a sort of open offer to follow up with investing in this kind of infrastructure locally and beyond. So lots of background with here, and I'm not sure what the format is, but if there's time, I'll be happy to take questions and discuss. Thank you.